Okay, so part 2 of the solar activity lecture. I asked you to go away and have a little read up about the Zeeman Effect. So this figure here from the universe textbook really shows the Zeeman Effect in action. It's a little bit complicated, but what you're seeing on the right-hand side is the key thing here. So this is actually a spectrum. So wavelength is going along this way, along the x-axis, if you like. Okay, and you can see that there are various spectral lines here. So spectral absorption lines, we'll come on to those later in the module, due to various elements. I think these are due to some iron lines. But going vertically is is basically a spatial change here. So on the left, you can see an image of a sunspot group, and the dark line here going up through is the entrance slit to the spectrograph. Okay, so you can, all the light going down this slit is ending up over here and spread out in wavelength this way. So basically, each row here is a spectrum along a different portion of along this slit here. So you can see that off the sunspot down the bottom here, you've just got these are just single lines. Let's focus on this one. This looks like a single dark absorption line. But as you move into the region where the magnetic field is strong, so on the sunspot here, suddenly you've got 3 spectral lines instead of 1 that there was before. Okay. And so this is exactly what the Zeeman effect is all about. Basically, when you put an atom in a very strong magnetic field, it breaks some of the degeneracy in the quantum levels, so the levels that the electron can occupy. And so what was a single quantum level in the atom gets split, so it could become 2 or 3 or many levels. And then if you've got more than one level to do a transition from by the electron, then it will generate more than one spectral line, depending on which of those split energy levels the electron started in. So that's the idea of the Zeeman effect, and basically you can measure the strength by the further apart these lines are, the stronger the field. And then if you superimpose on all of this also the polarization information of the light, so you can put it through a polarizer, which tells you basically if the electromagnetic waves are aligned in particular ways. You can then also work out the direction of the magnetic field, whether it's into the sun or towards us, away from us or towards us. So all of that information you can get from a combination of spectroscopy and polarization. So this is quite nice to see early on, actually, because it's really the essence of the kind of way in which astronomers have to work. Okay, you can't really, even though the sun is probably the nearest thing we'll talk about in this module, you can't really go into these sunspots and poke about with instruments and that kind of thing. All you get is the information that's coming to us in the radiation. And so you have to do everything you can possibly think of with the radiation in order to unravel the information that's there. So you can disperse it to take a spectrum. You can look at polarization to look at further information. You've got the spatial information, so you can start to put all this information together. So that's the real detective game that modern astrophysics is all about. Okay, but as I said, the details of Zeeman effect, it's not central to this module. So let's move on. Okay, so we were talking about the sunspots, and we talk about the sun rotating once every 30 days or so. But there's something stranger going on longer timescales, sort of every 10 years or so, and that's that the number of sunspots visible on the solar surface at any one time steadily changes over time. Okay, and so you can see that here in the diagram on the right. So you've got a long sort of time trace along the x-axis here. And basically just literally the number of sunspots visible at any one time plotted on the y-axis. And you can see that it just goes regularly up and down with a period of pretty much exactly 11 years. Okay. You know, sometimes they're higher, sometimes they're lower, but the period is always there. Okay. So that's what the solar cycle is all about. So it's the fact that the number of sunspots reaches a maximum on the sun every 11 years. And this, you know, this has been known for centuries now, goes all the way back here. In fact, there was a period before this that was somewhat unusual, referred to as the Maunder minimum, where the sun seemed to have no spots on it for many, many decades, and it coincided with unusually cold temperatures on the Earth, the explanation for which is not really understood, when the Thames froze over and all that kind of thing. But you know, this cycle is very, very steady, okay, most of the time. Okay. So we're gonna put a few observational facts about the solar cycle together first in this part, just quickly, and then come back finally to try and put it all together, to explain it all. So the next thing that is seen with the pattern of sunspots over this 11-year period is that this diagram here is called a butterfly diagram. And what it's plotting now is where on the sun the sunspots appear. So this is the latitude on the sun. So this would be the north pole of the sun, the rotational pole, if you like. This would be the south rotational pole, and this is the equator along the middle here. Okay. And so early on at the beginning of a cycle, the sunspots start out at fairly high latitudes. Okay, well, moderately high, 30 degrees. Something like the tropics equivalent on the Earth. Okay, so that's where most of the spots would appear. They don't appear near the equator at all early on. Over time, as the number builds up, you can see that on average, that the location of the spots gets closer and closer to the equator, maybe 10 degrees away from the equator, on both sides. Okay, so you see this pulling in of the spots towards the equator as the cycle goes on. And here the number starts to drop again, but you can see they're still tight into the equator. And then when the new cycle starts, as it does here, then they flip back up to the starting at high latitudes again. And the whole pattern repeats itself again. Okay. Something to also note here is that you very rarely see sunspots right on the equator. Okay, they're always just off one side or the other. So they're always basically, you know, in one hemisphere or the other. You won't see them crossing or anything like that. Okay. And the reason for the name of the butterfly diagram, as you can see here, if you like, then you know, it just looks a bit like a pattern that a butterfly's wings would make. So that's where the name comes from. Okay. Okay. Now, if we return to our Zeeman Effect diagrams, the magnetograms again, something else becomes apparent now. Okay, so this is another of these magnetograms, a bit like we saw before, but a slightly different projection now. So it's this is just a snapshot in time. So this is sunspots going all the way around the sun. Okay, so you're just taking your spherical distribution and unraveling them. Okay, and plotting them as a map, if you like. And so we've got basically latitude here and longitude here, if you like. So again, if we look at this top diagram, you can see the same polarity pattern that we've had before, now coded yellow and blue. So here the yellow ones are leading the blue ones, yellow ones leading the blue ones. And down below, a good one, yeah, the blue one is leading the yellow. Okay. Blue leading yellow, blue leading yellow. So that's the opposite polarities in opposite hemisphere pattern here. So that's in one particular 11-year cycle. Okay. If we go to the next, a snapshot in the next cycle, so this is now, say, 11 years later, you see that the whole pattern is switched over. Okay, so in this cycle, the yellow in the north, the yellow was leading the blue, but now it's the other way around. Blue is leading yellow, blue is leading yellow. There we go. And in the other hemisphere now, yellow is leading the blue, yellow is leading the blue. So it's the opposite to this. So actually, this whole polarity pattern has switched over from one 11-year cycle to the next 11-year cycle. So we wouldn't get back to this pattern for basically 22 years. Okay, so we'd have to go through all of this, 11 years of this, before we flipped back to that, getting back to that same pattern again. So you could really think of the solar cycle as being a 22-year cycle to really repeat its pattern. But in terms of numbers of sunspots, they go up and down with 11 years. In terms of the polarity pattern, it will only repeat itself every 22 years. Okay. So those are the observational facts of sunspots that we have to explain. Okay, so we've got the numbers going up and down, we've got the polarity pattern switching, and we've also got the latitude at which they appear decreasing over the cycle. Okay, so those are the things we need to explain, and we'll try and pull those together in some kind of model in the final part of this lecture. In between these two parts, it'd be nice if you could have a go at these two things. So perhaps have a go at finding out where we are right now in the solar cycle. So are we at a solar maximum or a solar minimum or somewhere in between? So see if you can look up that information or just extrapolate the graph from before. Another quite nice thing to do is to actually go and have a look and find out what the sun is up to today. So there are lots of satellites and ground-based observatories looking at the sun all the time. Quite a few of them are pulled together on this particular site, solarmonitor.org. So that's a good place, but there's several other places you can look for this as well. So go and have a look and see if you can find out what the status of the sunspot activity is today and whether it chimes with your answer to the first part. Okay, so see you on the other side of the break.